Hi, everyone. Thanks for joining our webinar today, titled Picking the Perfect Diffraction Dispersion System. My name is Brent Cunningham from HORIBA, your facilitator today, and I'll be monitoring any questions or comments you have in the background. We also will have a Q&A session in the end. It is my great honor to introduce you to our speaker, Dr. Jeff Bodycomb from HORIBA. Jeff is the product line manager for our particle characterization group, and he has decades of experience within particle analysis. He's given quite a few webinars here in the past. Welcome, Jeff.
Well, thanks, Brent. Thanks for the introduction. Today, I'd like to talk about kind of the other side of laser diffraction, which is getting the particles into the instrument for analysis. And so that's, and picking the right tool for the job really is a review of the different tools available, and can hopefully excite some thoughts about how to handle challenging samples. Quick overview of the talk. I'll give some introductory comments. I'll then talk about ways to handle liquid dispersions. I tried to order it from largest to smallest sample volumes. And then I will talk about how to handle dry powders, and I'll close up with some concluding comments and recommendations. I do have some biases about different sampling systems, and I will go ahead and telegraph them. One overall comment is that as you work with HORIBA, you can talk to our application experts, including myself, or have samples run, and we can certainly guide you through the selection, but this kind of gives you a sense of some of the questions you can ask. But back to an overall introduction, and I always like to give a little perspective. Particle characterization is a broad field, and a number of different analytical techniques. I like this chart where I showed particle diameter along the bottom, and then resolution of mixture components along the vertical axis. And laser diffraction, which is really the topic of today's talk, has things ranging in size from tens of nanometers up to about a millimeter or more. And so with such a broad size range, you can have a really broad range of surface effects that affect dispersion and so on. And the core measurement principle is we're going to send some light into a sample. We're going to look at the scattering as a function of angle to extract a particle size distribution, which is shown here on the right. And the LA960 has some pretty sophisticated optics. We actually have two light sources with two different wavelengths and a very broad angular range from 0.006 degrees to about 165 degrees, which lets us get from the largest particles that tend to have all the scattering excitement at small angles to the smallest particles where you want to make sure you have that wide angle scattering data as well. Now, HORIBA has been working with laser diffraction since well before the turn of the millennia, starting with kind of LA 500 was the earliest picture I could find. And then over the years, you'll see improvements, and you can see, well, if you dig into the history a bit, you'll find out that there were improvements in the data processing in computers, of course, along with the rest of society, optical improvements, and then finally sample handling improvements. And so all of those things have contributed to modern instruments. And today we're primarily talking about how do you get sample into the cell for measurement. And step one of that is you would separate your loose agglomerates. So you could start with your agglomerated particles, say that they just came out of a container and a little bit pressed together, or there's some electrostatic charges getting them to stick, and you just separate them into individual particles in order to make the measurement. So kind of step one in the sample handling is ensuring the particles are well dispersed. Sometimes that happens within the instrument, and sometimes that happens before you introduce the sample to the instrument. So kind of what things do drive decision for which sample handling do we pick? Well, kind of the First is the particle size, and where particle size will drive decisions is if you have very large particles, then your settling is going to be a consideration, and you'll want to make sure that your particles will remain entrained in the suspension versus having gravity just take them out of the measurement region. And as particles get to under 1 micron, dispersion effects become important because the surface area of the particle for small particles gets so large compared to the volume that surface energy effects become important, and loose agglomeration is something you really need to think about. Another thing to think about is the width of your size distribution. I'm going to kind of say something with a width over 3 decades or so is a very broad size distribution. And what's important there really is two things. One is when you go to take a sample with a broad size distribution, your sampling procedures and sample splitting becomes much more important. And the second is you want to make sure you look at enough particles during measurement to capture such a broad distribution. If you have all your particles the same size, exactly the same size like ball bearings, you measure one and you know the average already. But if there's a range of sizes, you need to measure more particles. The amount of material that's available is also very important as you pick sample handling. And if you don't have much material, that's going to be a very important measurement constraint. Sample form, which is kind of coupled with dispersion types. Do you have a dry powder or a liquid dispersion? And then if you want to make a dispersion, have a liquid dispersion, or you plan to make one, what dispersant or liquids are you using? So learning all these things will tell you or give you some pretty strong hints about what you want to use to make the analysis. I'm going to start with wet analysis, where there are lots of options, and I'm going to kind of walk through real quickly. There is a liter flow, which isn't shown in this image, but in this summary, you see a regular flow cell or a solid flow system, which I'll describe a bit more detail. I'll describe all of them in a bit more detail. Volumes of about 180 to 250 ml, and a size range is very broad. The mini flow is a smaller volume system at only 35 ml with a little bit more narrow size range. The fraction cell has a volume of 5 to 15 ml, so this is where you get to very small volumes. The size range here goes to 3 millimeters. I'm going to have a caveat about that as we get into the discussion later. Our paste cell, you need basically a few drops of liquid, same with the HL cell, both less than a mil, and you have more narrow size ranges. So let's get into details on liquids. And we are going to start kind of with the most popular type of circulation, which is what is in a stock instrument. We call it aqua flow or solva flow. So here I have the LA 960, and then I have superimposed an image of the flow system where you have a sample chamber on the right side here. You have a centrifugal pump, which is less abusive to particles, goes through and through a flow cell and recirculates back. We also have onboard ultrasound here. So if we're gentle in the pumping, and so if you need to break up loose agglomerates, you would use ultras. You can add energy with the ultrasound. We have an agitator as well, and the agitator is there in order to help keep particles entrained in suspension. This system has been tested with dense 3 millimeter particles, pretty much because we can. I mean, it was kind of an extreme experiment, which impressed me. But knowing the guys who did it, they just liked engineering over engineering things, so that's what they did. So the features of the system, very popular, least expensive, just about the least expensive way to go, and works for a broad range of applications. The volume 180 to 250 ml means you're going to need more sample than you will need with other sampling systems. and you're going to need more liquid. Water's usually pretty inexpensive. Solvents can be expensive, either in terms of purchase and disposal costs or in terms of safety. Having a larger volume makes it kind of easier to add sample because you need to add a decent amount to change the concentration, and so your liquid handling becomes easier. With all these pumps and automatic filling, which I didn't mention, but we have a fill pump on this and an automatic drain. You can just press a button and the system will rinse itself. Or you can tell around rinse 5 times. You press the button, it just keeps going. This can be used with our imaging accessory, and I'll mention that a little bit, along with the slurry sampler, another kind of sample handling accessory I'll mention. There is a solvent-resistant version, which you really need if you're using organic liquids, and it circulates even large, dense particles. So this is kind of a laundry list thing. This is the sample system I start with for everything, unless I'm told otherwise. So unless I hear, or I might ask if your sample is valuable, depending on what your application is. Sometimes it's just obvious. But if it looks like we have plenty of sample, this is what we deploy. When you send samples in the lab, which is kind of where these numbers come from, how much material do you need? And this gives you a sense of how much material is required for each of the sampling systems if you want to do some method development and run a few samples, just to give you a sense of the mass. Dry powders, probably 2 to 5 cubic centimeters of powder. And for liquid samples of kind of pre-dispersed particles, probably 10 to 20 ml of liquid. Again, that's not a single measurement. I mean, we've done measurements depending on the sample with much, much smaller masses or volumes of liquid. This is something where we feel very comfortable. And it gives us enough room to go on and do some light method development. Okay, now we have a larger volume system. And I mentioned earlier that if you're measuring a very broad distribution, you might need to look at a lot of particles. And the way to do that is you have kind of a maximum number of particles you can put into the system before you can't do a successful measurement. So you add more liquid to your system. There is an option with a volume of about 1 liter. This gets you data from very broad size distributions. This is a fairly rare option. One application that looks close are soil samples and sediments. But the reason I say it looks close is that in practice, that the regular solvent flow system has been working out fine. It is a sample that covers about 3.5 decades. But I think if we get to 4-decade or so distribution width, we're going to need the liter flow. So yeah, we're going to start thinking at this breadth, gee, do we need a larger sample volume? May not. And then if I get much more on this, we probably do. Wasn't really sure where to put the imaging in terms of sampling options. But it is something you can move in and out of the flow path, and it does get you different data. So I dropped it into the liquid side because it really works with liquid samples, where we really have an integrated camera. And the nice thing about imaging is you have pictures, and you can get a number-based size distribution with size range about 9 microns to about 1 millimeter, and pixel sizes are sub-micron. And so if you look at some of the standards on imaging systems, they say, well, 1 pixel is 1 particle. We're a little less convinced of that. Really, if you have a particle that's 1 pixel, it could be camera noise. And so that's why we set our spec at such a high particle size. Nice thing about this is that you can extract aspect ratio, circularity, convexity. Here's a different display of circularity for the same sample with more bins. Probably falls under the heading of sample handling in the sense it really is an accessory. It adds slightly to the volume of the system, but not much, and still lets you automatically clean the whole system. Another option that is relatively uncommon, but when people start running a large volume of samples, it becomes very important to them, and that is an auto sampler. And that is shown on the right-hand side here. So I have the instrument on the left and the auto sampler on the right. Now, this auto sampler, zoomed in plot here, has a couple things that are a little bit different from your typical, say, a GPC auto sampler, or where you just draw the liquid up, in that there is an impeller that stirs the sample and ensures that you've entrained all of the larger particles before you draw it into the system and then put it into the analyzer. An auto sampler, of course, the whole point, at least in my mind, is that as the auto sampler is running, you can sit back and drink coffee or do other useful work while your measurements are being done. And generally, these are deployed where you have a very large number of samples that you need to get run, and you set them all up, press the go button, and come back to some answers. Moving down in size is the mini flow, and this comes up in a couple different ways. So it's a smaller volume at 35 to 50 ml, and it slides into the instrument. So there are a couple nice things about this. The most obvious is that you have a much smaller volume. It's about a quarter of the volume. It still has the onboard fill pump and the ultrasound, and so measurement is fairly simple. It's solvent resistant, and this is where really the second feature comes in. So the first is, hey, I have less liquid. It means I need less sample, and that's great when you have valuable samples or valuable liquids. The second is that if you're swapping between aqueous and non-aqueous use, so if you're running water versus cyclohexane, for example, you would need to rinse the system with an intermediate solvent like alcohol or THF or something like that. And so switching between organic and aqueous, it takes a bit of time. What some people do, which is quite clever, is they'll use the aquaflow for all their aqueous work, and then they'll take out, they'll disconnect the cell, and they'll insert the mini flow for working with organic liquids. And they're two completely independent flow systems, and you don't have to rinse as you switch between organic versus aqueous. So this saves you a whole lot of time. You would use a smaller volume system for organics because organic liquids tend to be more expensive. So that's a second feature of having this. It's a bit like having a second instrument, and you dedicate one instrument to one application, another instrument to another application. And of course, in truth, it's the same optical bench, so there is a savings there. Moving further down in size is the fraction cell. This is a glass cuvette, and you can think of it as a funny shaped square beaker. The mixing is only a stir bar, and our smallest volume, the 5 mLs, don't even have a stir bar. So for dry powders, we're looking at kind of 1/10 the amount of material, 0.2 to 0.5 cubic centimeters of powder, and 1 to 2 ml of liquid sample. So much, much less sample required, and that's really where the fraction cell shines, or is when your samples are quite valuable. You do have to kind of take it apart or take it out and wash it manually. There's no autofill, obviously, to save liquid. This is also where this question of particle size and celling becomes very pointy. Now, here's some data that was done looking at laser diffraction and the repeatability, and the limits kind of increase with decreasing size. So you have a non-acceptable regime where for larger particles, your relative standard deviation has to be less than 10%. And these are real samples, so you're actually including other effects beyond the analyzer. And then for the smaller ones, we can let the relative standard deviation go to 20%. For a number of samples at this customer lab, they found that there was non-acceptable ones. when they removed the points from the non-acceptable region that were generated with the diffraction cell, there was only one left. So the take-home lesson on this was the diffraction cell really wasn't stirring the samples well enough to get good, repeatable data. And this is kind of where I made my comment about 10 microns and selling becoming significant. So when things get to be over about 10 microns, you kind of want to convince yourself that your sample behaves well before you go to the more gentle stirring of the fraction cell compared to the more powerful stirring in the mini flow and solver flow systems. So kind of closing comments on that. Upper size limit depends on density, but avoid it if you have sizes over 10 microns. And so that's something where we're going to start keeping that in mind as we're measuring samples and think about how to run it. We also have high concentration cells, and the volumes are very small, 1/2 to 2 mLs of total cell volume, which is nothing compared to a solid flow. The trade-off, of course, is that the setup and cleaning becomes more difficult. Now you're taking the cells apart and cleaning each of the glass plates. And so there's more dexterity required and less button pressing. It's important to minimize the bubbles. Generally, people like this if nothing else will do the job. So if you have just a small amount of sample, or if you're interested in higher particle concentrations, this is how you want to do it. I mentioned higher particle concentration, and this is kind of a fun effect, so I'd like to talk about it. On the HL cell, you have a window, a spacer, and a window. And it's a very, very narrow spacer with a very short optical path length. If you think about scattering or a scattering experiment, what you want to do is have light strike a particle and scatter and nothing else gets in the way. So if your particle concentration gets to be too high, you can kind of have two sets of effects. One set of effects is that as the concentration gets higher, you're going to have contact between particles or chemistry happening, and optics can't fix any of that. The other is that as you have more and more particles, the probability of secondary scattering gets higher and higher. And by taking the typical long path length and making it very, very short in the HL cell, like I show on the right, now I have light strikes a particle and it leaves before it has a chance to find any other particles. And so it's really the short path length that lets me get to the higher particle concentrations. Mechanics of use, just kind of full disclosure here, window, a spacer, a flash gasket, and second window. You put that assembly together, and then you fill it using two syringes, really lure type syringes. This doesn't have the bubble issues of the paste cell, because, well, I should say you can suppress them with clever use of syringes. So it is an improvement. So here is some example data, kind of talking about why you might do this. So I have a battery electrode and proprietary material, and sample 1 and sample 2 had different performance in the battery. And so this is so you had two different suspensions. If you dilute 1 to 4, you could see a significant difference in particle size in the HL cell. If you dilute 1000x, so your particles were well separated and you could work with a larger volume system like the solver flow or a fraction cell, you would see the same particle sizes. So the dilution or the high dilution was suppressing the aggregation that was actually interesting to the customer in this case. And so here's a case where you would kind of put up with the cleaning in order to get the data at higher concentrations. Now, LA960 has multiple configurations. You kind of have a main analyzer and you would add other pieces to it. So if I move to the right, you can see the camera system in the upper corner of the instrument. The door still closes. You can't even tell it's there once it's plugged in. You could remove the sample tray and slide in the mini flow. And the other option is to put a dry powder feeder on top. I mentioned the sample tray without defining it, which is a bit naughty, so let me fix that. The way we set up the system is you have a tray and you can put up to 3 different cells, and to switch between cells, you just open the door and push or pull the tray to slide the correct cell into position. And then there are pins to ensure that the cell gets into the right position as you move it. And so you'll have quite often the dry tower on the back. You might have the regular flow cell in the middle, and a paste cell or fraction cell at the end closest to you for easy access. And so when you change modes, quite often it's a matter of open the door, slide, restart the software, and away you go. So here's another kind of schematic of how you just reach your hand in and slide it forward or backwards. So one of the points of this is that you have the fewest steps and the least chance of making a mistake or losing a bunch of time when you have to change the type of measurement. Now, I mentioned this dried powder dispersion on top. And so let's talk a little bit about that. So it kind of does what it says on the cover. This is what you would use when you have a dry powder sample and you want to run it in air. It's going to have windows, has metal sheets, and compressed air. So the compressed air is going to come down around the outside, and it's going to go through these metal sheets and create a buffer zone between the particles and the glass windows. And this really gets you 2 things. The first is that it keeps the windows clean. The particles don't go out to the windows, and that's really convenient because it means you can make multiple runs without having to worry about dirty windows. The second is it kind of narrows the range where the particles fall, and that will let you get better measurement data. Now, the system has direct flow of powder straight down, so you don't have to make any turns, which means you can be quite gentle with the powders if you desire. It also has a compressed air feed, and as you increase your air pressure, you can start to have dispersion effects and really break up your loose agglomerates. And you don't have any impact surfaces where the particles will recombine. There's a feedback control on the system, which gives you good reproducibility, because if you have too many particles coming off the chute, then you could have your transmittance go too low. That is, you have too much scattering and you get multiple scattering effects and so on. And so you want to slow down your feed, and the system does it for you. We can work with as little as 5 megs of sample. Generally don't recommend it, but it can be done. I'll mention a sample volume later. You do need a sample that flows okay. And so this is a tool for dry powders. You could break up agglomerates with the air pressure, but if you have a sticky mess, it's going to be a sticky mess just even getting it off the hopper. The other comment is that particles under 1 micron have a relatively large surface area, and so those particles can be very difficult to separate unless you use something like a surfactant or liquid rather than just air to keep the particles apart. So like to use that for kind of larger particle sizes. I mentioned the feedback control. So you can set an initial speed, and you can set a target transmittance or obscuration, and let the system decide how fast to feed. This means you're less dependent on how the operator loads a sample into the hopper, and it gets you better repeatability. So for example, this is mag stearate, run dry, 2-bar air pressure, and my D50 is 8.23 microns, and there's coefficient variation about 0.3%. So you get very, very tight repeatability. And this repeatability really rests on 2 things. The first is a nice method and a good repeatable instrument, and the second is good sampling, where you make sure you riffle your samples. This is dry cement, doing reproducibility, D50 about 11 microns, coefficient variation 0.24%. And I think that was off of different bottles. How much material? Large, broad distributions require larger sample quantity. In fact, the dry powder feeder is very nice when you want to run a lot of material. You kind of load it up and let it go. We can get down to about 5 milligrams of material over a number of particle sizes, but again, most people don't run it that way. If the hopper gets to be an issue, we also have a sniffer option where you're going, rather than try to feed the particles in automatically, particularly if they don't feed well, you can use a vacuum effect to pull the particles off of a notched tray, and that's what's shown here. So generally, this is something that would come up when we do sample testing in the applications lab, which way of feeding is best. Our go-to option is the normal dry powder feeder hopper that kind of looks like this. So that is the most popular. This is more for some edge cases. Okay, so I hope I've kind of gone through the disperser options and other accessories for the LA960. And it really is part of a good measurement is not just the optical bench, but getting the sample there in a way that is reasonable for you economically and gets you good data. Kind of quick summary, we have our probably least common is liter flow. And you really need 5 to 10 cubic centimeters of powder or 25 to 40 ml of concentrated dispersion for method development. A single sample, you could probably get by with 1 ml for many samples. And the solva flow is about a quarter that size and uses about a quarter of that much dispersion for single measurements. Generally, the lab likes to look for 10 to 20 ml, again, for method development. Mini flow, even less material, 35 to 50 ml. And here we're looking at kind of a few hundred microliters of concentrated material. The fraction cell, 100 microliters at 5 to 15 ml. And then sometimes you'll get a dilute sample and you can measure all of it in a fraction cell. So if you have a very dilute suspension, this might be the way to go so you don't use up all your suspension. HL and paste cells, less than a mil of concentrated sample. Really, we're starting to talk about drops here. And for high viscosity or high concentration samples. And dry powder feeders, you might start with 5 to 15 cc of powder, but we run like less than 1 ml of glass beads when we check these systems, less than 1 cubic centimeter. So for a single run, you don't need this much material. But again, the numbers on the right are really ways to get a scale of how much material you might want to get going. And you have your system volumes and your options, what each is going to take in terms of liquid and sample. As you talk to us, or as you think about your measurements, you think about which of these options make the most sense. And generally, you'll have some overriding concern that will push you one way or the other along this table. If sample is precious, it's probably going to push you to the fraction cell pretty quickly. If you have a nice dry powder that's flowing well, dry powder feeder, you don't have to mess around with liquids. If you kind of middle of the road or you're not really sure, you'll start with the aquaflow or solva flow. It's so popular, and a lot of that's because it works for so many different applications. I think this is it is everything. So I think we're gonna stop here a little early and open the floor for questions.
Thanks, Jeff. It's a great presentation. We do have some time for Q&A. Which dispersion system do you see is the most popular?
Yeah, okay, good question. I mean, the short answer is the aquaflow. So the most popular system is this 180 to 250 ml aqueous-based systems. That's always an interesting question because it's kind of like, where do you start when you don't really know what's going on? If you already know everything about your sample, it's pretty easy, but when you're stumbling around, where do you start? And this is really where I start. I like water, and I will try to find a surfactant system so I can avoid using solvents. Excuse me. Because it's just so much easier to work with safety-wise and less expensive. So that pushes me towards Aquaflow. And then most of the time I have enough sample to run it, and it washes itself for me, and I really like that. Yeah, that's my first choice. Second would be the SolvoFlow, where I can run solvents as well. And our demonstration lab and demonstration instruments all have the solvent-resistant capability, because it does come up reasonably often.
Okay, thanks for that, Jeff. We got another one coming in. Could the air pressure in the dry powder feeder cause a milling effect to the particles?
Great question. Yes. And so I should have pulled up some other graphs for this talk, but if you have a high enough air pressure and sufficiently delicate particles, then you can have milling effects, and where your particle size just is going down because you have so much air pressure. The dry powder feeder lets you adjust the air pressure, and you can adjust that in the condition file. You don't have to turn a knob or anything, so the system does it for you. So you'll adjust the air pressure depending on the sample. Now, that gets back to why do I ask for so much material here? And that's because we might need to do some method development. We'll try some different air pressures and see which ones don't mill the sample. So you kind of see a small pressure, and then the size drops a lot, and you raise the pressure, and the size is kind of the same, and you raise it even higher, and it starts and the size gets smaller with high pressures. And so yeah, so you'll have to do a pressure titration in order, and some method development in order to use that dry powder feeder effectively. That also applies, or that same idea also applies to ultrasound. And so if you have the SolvoFlow or the MiniFlow, then the ultrasound to break up dispersions can also really break up your particles. If you want to have some fun, put an emulsion in there, just a liposomal sample or something like that, and then hit with ultrasound, and you'll have all sorts of havoc breaking loose in your system. Yeah, so you gotta watch as you dump energy into your system that you're not destroying your particles. Great question, thank you.
Great, thanks for that answer, Jeff. We do have time for one more question, the last minute one come in.
Yeah.
How can you determine the difference between particle damage from ultrasonication and breaking up particle agglomerations?
Okay, I'm gonna plead for some patience a bit. I'm gonna see if I can find that graph.
While Dr. Jeff looks for that, I will say that if you're not following us already on LinkedIn, we'll post webinar replays, any application notes that we publish. It's a really good source for any new content that we're putting out there. So you can find us at HORIBA Particle Characterization Group on LinkedIn.
All right, how can you determine the difference between particle break from ultrasound and particle agglomeration? Let me go back one slide, sorry. So first, somehow, one or the other, you need to decide a refractive index and get your sampling right, so that you when you repeat measurements, if you measure the same sample, you're getting the same number twice. You may not be happy with the number, but at least you're getting this repeatability. Now, as I add energy to a system, I plot size on the left and energy across the x-axis. So ideally, we think, oh, gee, I have some loose agglomerates, I add some energy, my median size is going to drop, it's going to settle down, and then I add a lot more energy, I can mill my particles. And in truth, so you want to make a plot like this, find that flat spot and say, okay, this is where we want to operate, is this flat spot. And this applies for either air pressure or ultrasound. What really happens is that this kind of stair-step effect is smoothed out. And so you're going to have to pick where the slope is minimized rather than where it actually falls to, where it actually goes horizontal. Because what's going to happen is in our mind, we say, oh, I have some agglomerates. I add the air pressure, agglomerates break up, but my particles are fine. In truth, you add some air pressure, the agglomerates break up, but a few of the particles also get broken. And then when I go too high on the air pressure, all my particles are broken. And so that's what leads to softening steps, the softening of the slope. And you're going to find yourself doing these sorts of pressure titrations where you're comparing your data with different air pressures. As example, gosh, I don't have the notes up, so I can't see exactly which one was which, but it goes 78, median size 78 to 65 microns to 56. And you'll start asking yourself questions about repeatability and believability of the results. Like this first one, you can see that far right peak, that's breaking up. And then so this must be an agglomerate. And then you can see that disappear. So I'd probably pick the highest pressure where I've completely suppressed the agglomerate peak. There's another example of mag stearate, high pressure. And this data is back when we didn't give you individual pressure numbers. 7.5 to 8.1 to 8.6. So between mid and low is good pressure, and the size dropped pretty dramatically. So it's 0.5 from low to mid, and then 0.6 from mid to high. So you're going to operate between mid and low, and then you'll probably decide which is most repeatable. Yeah, the newer systems, and here newer means like within the last 5-8 years, gives you more than 3 levels, and so you can. This is D90, D50, D10, you can add more points to see how level these plots get. And so this is a repeatability. I think what happened here is that the 3-bar pressure gave the most repeatable result. And so that's what we chose, more based on repeatability than breakage or the breaking up agglomerates. So this is one of the worst cases because mag stearate's a fairly soft particle. If you get a ceramic, you could do anything you want. Those particles aren't going to break, and then you do get kind of nice looking shelves. I hope that helps. Yeah, if you have a dry powder feeder, have an issue or a question, you can reach out to us, and I'll turn Amy loose and kind of clear up your application. You know, we do that. I'm sorry, Amy is our applications lab manager. She's been doing this forever as well.
Absolutely a great resource. Again, you can reach out to us, labinfo@horiba.com. With that, I would say thank you, everybody, for attending. Please make sure to join our newsletter if you're not already signed up for that, and look out for our further webinars that we'll be producing in the coming months. So thank you, everyone, again. Thank you, Dr. Jeff, and we'll see everyone next time.
Oh, thanks for listening. Okay, take care, everybody.